And welcome back for our final keynote. I would love for you to participate. Any questions and comments are more than welcome. We're going to talk about smart factories. They will be a very big thing in the upcoming 10 years. And our speaker proposes a new angle of looking at these smart factories with AI and wireless networking and has written a number of papers on this subject. From the University of Seoul, Florida, KC Chen. KC, welcome.
It's my pleasure to give this talk and about the vast network artificial intelligence in smart factories. First of all, I have to thank the research support from Cyber Florida and the U.S. Air Force. The first question is what is a smart factory? But then we have to go back to Industry 3.0, and I call it factory automations. Basically, the at that time we have some kind of fixed production line. As I took some photo from the internet and to show the situations, and the importance, of course, for the smarter manufacturing technology is definitely needed, and probably I don't need to address. What is the industry 4.0? Okay, and so in this case, we are totally introduced the smart manufacturing and also the Internet of Things. So the Industry 4.0 basically is very critical for future digital society, and particularly post the COVID-19 era. So it's a kind of combination of the AI computing and the Internet wireless networks, and of course the intelligent control, including the ambient sensing. And the in that situation, we have to rely on the different robots, and then I show the in the up figures is actually a kind of the many production robot, and the bottom is actually from the Amazon. It's like I call it a transportation robots. So in these situations, we may view the smart manufacturing from a global view is first is actually try to have the real time and the perfect match between the supply and demand, and leveraging the existing the e-commerce platform over the internet, and there'll be also involved the logistic of the raw materials and also the components, and which is another kind of the big challenge. For the smart factory alone, it's including the reconfigurable productions. So instead of the fixed production line, it's actually reconfigurable productions, and that will be able to flexible manufacturing products. And this also is kind of the dynamic, but in the meantime, we want it to be optimal. If not possible to be optimal, and at least we want to be near the optimal. Another issue usually people ignore is about the energy efficiency. That is another critical point. And finally, it got to be resilient to the cyber or physical point value. That is actually a kind of the challenge once we have the flexible productions. So this involved so many different kind of the technology that is a multidisciplinary knowledge. First is the AI computing, and then we have the distributed wireless computing, and it's also required ultra low latency wireless networking, and of course the network control, and that will also involve the cyber physical security and resilience. So in the following, I would try to use my recent papers, which is in a year ago, almost a year ago, in the proceedings of IEEE, about the wireless network multi-robot system in smart factories. And let me continue for more details. So we'll look into the smart manufacturing. So we actually can have this kind of figures. At the left hand side is actually we have to leverage the cloud platform over the internet. And at the right hand side within the green box is actually means that we have the smart factories. So that will be involve the edge network, and of course then the edge computing and edge AI, and conduct with the to work with together and try to for the production robot for the flexible productions, and which also require the transportation robot and the sensor and to work together. So in this scenario, and we may note a very special feature in a smart factory, which means there will be at least two kinds of the multi-robot systems. The first one is for the production robot, and second is transportation robots. So the typical example is the AGV in the factories as the transportation robot. So in this case, we try to turn our focus into the multi-robot systems. So as I mentioned, there will be two kinds of robot. Once we have the multi-robot system, the first question will be what is the multi-robot test assignment, and how can we proceed them in a very efficient way? This problem has been well studied in Industry 3.0, and I 2 years was probably 1 to 2 years ago, I have a book about the artificial intelligence in wireless robotics. Actually, in the chapter 10, there will be some initial introductions about this problem. And so the book is available in Attribute Explored, and so actually you can see the more detail, and there'll be lots of the good papers and books talking about this. But what's new for the in the smart factory for the multi-robot test assignment? Let me try to consider this way is first, how can we look into the problem? We can probably look from the temporal spatial graphic modeling, which means we have to not only consider the robot itself, is also consider the time flow, and therefore this kind of the sequence of actions in different times. And so the difference between the multi-robot text assignment in a smart factory can be we can see from this figure. At the left-hand side is actually for Industry 3.0. So we have the robot, different kind of the robot. So I put down with a different kind of the tools. So we have different kind of robot, and then fixed production lines, and then we can try to manufacture something. But if we have the same set of the production robot in the smart factory or for Industry 4.0, and then we can have the flexible productions for different kind of products at the same time. So in this case, there will be a challenge for the multi-robot test assignment, because when we look into the literatures, there will be really very limited number of the efforts try to look into the MRTA in the smart factories. So in this case, I have two particular mentions. When we try to proceed this kind of multi-robot test assignment, because the flexibility in terms of manufacturing, so we got to use the wireless networks to instruct the robots and try to work with the robots, and such that all the AI functions can be complete. And so in these situations, without the ultra reliable and the low latency wireless networking, the MRTA in a smart factory is not possible. So we can look into what is the MRTA in this case for the smart factories. If we look into more carefully, we may find out this is actually a complicated problem which involves the cyber and also physical. So this is a typical cyber and physical system. So we can consider this way. We have the robot to do the manufacturing. This is, of course, a kind of the physical system. But in the meantime, we have the AI and also WAS system, and it's actually have the to form the cyber domain of operations. So in this case, the test assignment in the smart factory is actually dynamics rather than a kind of fixed assignment. So this dynamics MRTA got to meet the requirement from the for the demand and the supply. And we can also further look into the problem, because different from the traditional MRTA in the fixed production line. This is actually a multi-objective optimizations that would include the throughput, the energy efficiency, and also resilience. So given the flexible supply and demand requirement. So in this case, we have the two domain of the cyber domain and physical domain. So this makes the problem become much more complicated. And some people would say, okay, can we use the deep learning? The answer is yes and no. Part of the reason is there will be a lot of the constraints for the practical use, and particularly we might not have the big data. Big data are available to train the deep learning. So we have to look into something from the different angle. This is what I call the network AI. The network AI, basically we can consider, this is the right hand side, there's the figures. There will be two robots, and then if we have the two robots, we connect them together with wireless communication, and each of them is going to deal with the environment. And then this is a kind of the new scenario for the AI. So in this case, even the communication will be totally different from the traditional what we know about the 3G, 4G, 5G communications. Because in the past, the communication is still with human to human, and right now the communication here is between machine to machines. Okay. So the first, we can see how can we model the a robot, and a typical case is we can use some kind of reinforced learning. In the machine learning, basically we have the supervised learning, unsupervised learning, and also the reinforced learning. So the reinforced learning is probably a good way to view the this kind of the interaction between the robot and the environments. And what is the challenge in this case? And we can consider from several aspects. The first is about the communication side for the wireless networks. So in this case, we probably think about, well, if that's easy, and then we just let a robot to robot to communicate each other, and then or sometimes in AI we call it agent to agents. But in this case, if everyone know about the wireless networks and they realize this might not be a realistic approach, the reason is the scalability. Actually, 20 years ago, it has been proven that the steady throughput of the this kind of 800 workings, once we scaled, and then the scaled throughput is actually dropped to zero. So in this case, we have to use a kind of structures, which is the basic consideration in this talk, is we are from the robot to the infrastructure and then to the robot. Because by this way, we have the two hop communications, uplink and downlinks, and then we leverage the infrastructures, and then we can eliminate the scalability issues. The second issue is about the agent computings. So the agent got to use machine learning and try to, based on its own observation and also the environment information from the edge. So in this case, there will be a kind of the partially observed machine learning. So what is a partially observed state is actually, we can go this way, is suppose this is agents, and then we have the environment. And unfortunately, the agent could not fully observe and or completely reserve about the environments. So the agent has to estimate about what's happening. So this is a partially observed state, and then it's actually create some kind of challenge for the AI computings. And of course, we can try to leverage since we introduce the infrastructure, then we can uh, introduce the agent AI and then to assist the operations. So once we have the partially observed reinforced learning, and then we have the local state, but that will be not enough. And then we need to consider the global state, which means the global interactions. But unfortunately, it's not possible to fully observe the global situations for any robots. So in this case, this is a typical partially observable machine learning. And we also need to introduce the wireless communications, and the purpose is very simple, because such that the robot can collaborate each others. So in this case, we have to know about the belief of the state, no matter for the partner or for any kind of target robots. And then we need to also update about what's the belief for the target's policy. And then in this case, each agent has to use a more advanced version of the reinforced learning. For example, in this case, we have to use the active critic as a basic fundamental mechanism. And we probably need to have the more mature learning algorithm, and such that we can provide the prediction about the other agents. So all this require a lot of the information through the networks, and unfortunately these robots are moving, so therefore it can be only done by the wireless networking. So we use a very simple examples. In this case, we have some kind of maze-like implementations, and then we have the two agents, agent one and agent two. They collaborate each others, and they try to block the moving of the target, the rest stop. And so in these situations, these collaborative agents is actually competing with the target. So they can only move in this kind of the maze environment. So there will be some kind of access, and then once the target moving out, and then the targets actually win. So we try to use this toy example and try to show the entire mechanism about the network AI. So the result is actually very interesting. So in this simple example, if each robot, if we go back to this one for the agent one and two, if they just work based on themselves, and they actually there's no possibility can reach the goal and try to catch or try to block this the rest stop. But by using communication, then the job can be done. So we can see the significant value for the communications. But if we can introduce the some kind of prediction mechanism about the robots, no matters for the partner, of course, we can exchange the information, and for the competition robots, and then we can actually provide the predictions, and then it will be much better. So in this case, that will be even more effective. So in this case, what we learn is about the importance of the communication in this kind of multi-robot system. And in this case, we actually conduct a series of the studies, as we mentioned in the buttons. There will be a series of papers, and try to explore about these issues. So we find out the importance of the communication for AI. The major reason is the communication can allow the AI computing to be more effective and more efficient. But on the other way is this is a totally new traffic into the communications. So in by this way, and we probably would say, okay, we thought if we try to use traditional human-to-human communication to cover the machine-to-machine communication, this is probably not possible, or at least it is not very efficient. And there'll be even more challenge because if we try to conduct the man-machine collaborations, so because the robot cannot really communicate with the human beings, so in these situations, and then the AI computing has become much more complicated, and so that's why we in early example we have the target uh, which cannot communicate with the other agent and the other robots. And also the another issue is about we keep talking about the latency. Why the latency is very important, because that would be related to reliability. So thank you for Dr. Zhang, actually who was visiting my lab a few years ago. So he drew this figure for me, and so traditionally we have the green line for the let's say Slati Aloha. But if we increase a dimension about reliability, which means that within certain time we got to get the information, and then we suddenly realize the traditional way is actually looking to the green curve, and what we really want for the machine-to-machine communication is the blue curves. So this is a pretty much quite different stories. So there will be quite a few fundamental issues about machine-to-machines, and of course machine-to-machine 2.0 is first is what to communicate. For the AI computing, we probably need to understand about the reward map, states, policies, and we got to do it very frequently. In to the state of the art robot, we are talking about 10 milliseconds. The robot got to make a decisions, or in many cases, that'll be even 1 milliseconds. And then how can we communicate? And this is a quite different story. And of course, how can we use the communications and try to facilitate the more efficient and the more effective AI computing? That is a kind of new subject. And for this subject, I try to introduce a new name. It is the communication for AI instead of the AI for communications. So in this case, we have the collaborative robots that will require the extensive high quality communications into our smart factories. So in this case, what do we say the collaboratives? So that means that each robot has all the robot has a common goal, and we have they have to collaborate with the other robot to reach the common goal. However, each robot has its own AI and based on the locally available informations. And so in this way, it's not possible we have the centralized control for all the robot for every actions. In reality, that will require tremendous amount of the data collection and the computation that is not possible to be done in the real time. So in this case, that will be even further because one big problem is from the partially observed environment because each robot has its own localizations, or we may consider it's a robot pose, and therefore its own coordinate systems. So if we have the N robot, that means there will be N coordinate systems. They are not perfectly aligned, and there'll be even further. And actually, we have the global, which is the true coordinate systems. So this is actually create a tremendous challenge because of this partially observed feature. So let's come back to the multi-robot test assignment and the location, and how can we precisely proceed the job. So the way we can actually do it is as we already can see at the right hand side for the figures. So we may based on the demand, and we may adjust the dynamic adjust the production flow for the text assignment. So in this case, it got to be reconfigurable, and then such that we can have achieve the high flexibilities, and then we can accommodate the frequency adjustments and of the productions, and then we can have the system optimization, and then we try to reach the robust and resilient operations. So that would be the goal for the MRTA. So how can we proceed? Actually, we look into the problem. So this is again, we just mentioned about the temporal spatial collaborations. So we look into this problem. So let's try to focus on the figure at the right hand side. So suppose we have different types of the robot, and for example, the type 1 we have 3 robots, and so we can label them. And for the type 3 we have 4 robots, and we can actually label them. So the multi-robot test assignment in this case is try to find out the way we can complete the test, and then this factory would have the maximum throughput. The maximum throughput, that means the maximum production output. But in the meantime, there'll be something very critical because the energy efficiency is actually very critical, and also we need to consider the time to transport between the robots. So this will be another issue called energy efficiency. So this actually create the problem. So the solution for us is we propose a kind of the hypergraphic approach, and for the real-time MRTA. So we can see from the right hand side, so we have this kind of production possibility, and then we can actually create the hypergraph. The nice part for the hypergraph is allow the robot for multitasking that is pretty much aligned with the true story in the smart factories. And so, for example, the one robot can handle the multiple tasks at the same time. So now the challenge is how can we find out the optimal text assignment in this hypergraph? So the basic principle for AI is then okay, then we can conduct the search, and so there will be a hypergraphical search. That is a relatively new problems. So in this case, the purpose of the MRTA is try to transform the production demand into the test assignment for each production robots. So the classical way is first that is a fixed assignment. Second is we try to find the optimal value. But if we try to this is kind of very dynamic text assignment, and then we got to have the real time solutions. So that will be kind of the big challenge. So how can we proceed? So what we are going to do is first we can model it as the constraint specification problem. So that is a typical ways. But then this computation, because we got to finish in the real time, this is a really once the number of robots grow to some big numbers, let's say the 100 or several hundreds, and that will become almost impossible to be done in real time. But on the other way is we do expect there will be hundreds of robots or even more in a smart factory. So what can we do is we try to look into the maximum floor heuristics, and then we try to optimize the productivity. But in the meantime, we try to conduct with the explain greedy first heuristics, and then we try to optimize the energy efficiency. So by this way, we can actually try to provide the real-time MRTA. But at the price, we may lose the optimality, but what our goal is try to reach some kind of assignment can be done in real time, but very close to the optimal point. So we conduct some computer simulations. This is considered both for the energy and for the throughput. And then we will see, okay, there will be several points. And this is actually very nonlinear, as we can see from the top figures, very nonlinear performance. But we also know something very interesting, because we look into the possible solutions, and then I told my student, this is great because we can develop the concept. I call it a permissible solutions, which means there will be only a small set of the possible assignment we should consider, and then we optimize. Instead, we try to search the entire space. So in this case, actually, we can get very effective computations. Then the next question is, well, the throughput is not everything, because we have to consider how can we have the high yield for the productions. So in this case, we have to consider the further into the test assignment and the decision behavior in the multi-robot systems. So the one of this is based on the sequential actions. In this kind of sequential actions, and we actually have a series of papers, and it's all in the IEEE publication, and we can find from the IEEE Explore. The idea is go this way. We already mentioned this is a kind of the cyber physical system. So if we look into these two parts, and we may find out we actually have the cyber domain for the AI and the networking, wireless networking, and then we have the physical domain for this robot, interactive robot, and they're going to collaborate each others. And there's a particular point I want to raise. In the past, people usually consider the topology connection will be the same in the cyber domain and the physical domain. But here, we try to, if we look into the figures, it's actually they can be different, and practically, I think they would be quite different. So this actually create a very interesting problem for us, another new problem for us to try to look into. So, and also in terms of the production process, that will be a kind of the sequential decision for in this multi-robot production floor. So that means we look into the problem. We are actually having I call it interactive decision in this kind of multi-robot systems. So in this case, this is not, if we try to consider this is a single shot decision for each robot, that would be totally wrong. And the reason I got this idea is actually one of my classmates who runs the company and very successful in today's electronic manufacturing. And actually, then what I realized how important in the production step, from one step to each for the next step. And the alignment between these two steps will be very critical. So which means the production for the robot, if we in the production floor, if we had the production A try to finish the job and production B try to finish the next job, and the alignment between robot A and robot B is probably more important than their global precisions, because this is kind of decision they are going to the kind of the interactions. So how can we deal with this problem? Of course, we try to use in AI, but there will be a quite different concept of the AI, and we introduced the concept called the social learning. The social learning is actually from the kind of study from the social networks, and we can consider if there will be a group of rational agents, and how can they make a sequential decisions. And in this case, actually, there's a famous problem called the information cascade. Uh, it's very interesting. Information cascade considered to lead into some nerd behaviors, and is probably not preferred in the social networks. But however, the information cascade can be very useful in the multi-robot system, because if the multi-robot system they are perfectly aligned and by some sort of the information cascade, and then the efficiency will be great. So in this case, we can apply the social learning to further enhance the performance of the multi-robot systems. And by the way, we also know that something very important is that network topology play an important role. We actually study at the very beginning a few years ago, when the first time my student told me the result, I was totally surprised. And the fully connected topology is not necessarily good. And the reason is actually, after all, become very clear is that if the fully connected topology may bring in noise and could not increase the informations. Okay, so this is something very interesting. So based on this concept, and actually we can develop and look into the production behavior. So we can see without the social learning and the in terms of the robustness in the production actually drop quickly. But however, if we can try to introduce the social learning, actually we can extend the operation region quite a lot, and this is very critical in terms of the productions. And that would be further. And how can we leverage this concept and to develop the alignment of the robot toward the high years? And so the first is we got to make sure, because a temporary collaboration robot teams is actually roughly means that the robot teams in the same alignment production floor. And also we probably don't want to align to the global reference, because they need to match each others. Okay, and so in this case, this is kind of a new problem, and in terms of productions. So the other challenge is, and but in the meantime, how can we develop the resilient MRTA against the possible error, particularly for the cyber error or any point value in the dynamic operations? So in this case, we can what we need to introduce is we try to form very careful the estimation structures, and then we can introduce the basic network and try to achieve the coordinations among the distributed social learning and of the multi-robot systems. And so based on this, and then we can tie together. If you see from the figures, actually we have based on the local evidence and the social evidence, which is actually collect the information from the sensor, from the onboard sensor, and from the environment sensor, and then the robot need to construct the basic network, and then try to have the maximum likelihood estimation, and to form the local belief, and such that its AI algorithm can be more efficient. So we do provide some kind of the computational experiments. So you can see in the bottom of the figures, and you can see some red dot line, which means the production has been changed. And if you see, we can also see some green dot line, which means there will be some kind of the injection of the cyber error or the physical error, and then see the performance. So the blue mechanism is we just follow the traditional approach, and then the orange one is we actually conduct the mechanism in the earlier slide, and we can see that is going to provide significant resilience to against the any production transitions and also any potential error. So this is actually pretty robust and resilient operation, the MRTA, the multi-robust system operations. So of course, what we have been introduced is just a few kind of new concept. And I would say the wireless network, the multi-robust system in the smart factories is actually an emerging scenario for AI and 6G. So this is actually the photo I took from the pond behind my house, and you guys see a tiny look like the alligator in the pond. Actually, that is a pretty big alligators. Okay, so at this moment we just see a little bit about the technology. There will be much more we are going to develop in the futures that we rely on the entire community to work together. So that's pretty much my presentation. Thank you for your attention. And this is the sunny Florida.